Hello and welcome to the first talk in what we hope will be a wonderful virtual OOPSLA. My name is Stephen Ellis, and today we'll be looking at translating generic Go to Go. This work was conducted by myself, Shofei, Nobuko, and Linhai. Go is a popular industry programming language created in 2009 by Google and is used by the likes of Uber, Docker, and Kubernetes, to name but a few. Unfortunately, the language's lack of generics has been a pain point for many years. Of the respondents to the 2020 Go Developer Survey who said that Go was missing a critical feature that they needed, 88% pointed to the lack of generics, or about a fifth of all surveyed users. This was far higher than those who required better error handling or even null safety. So how do we correctly and efficiently implement generics in Go? Recently, the Go team have made significant strides in introducing generics into Go, but by their own admission, this work is far from complete. Beginning in earnest with the Theory First Featherweight Go paper presented in OOPSLA 2020, this work formalized monomorphization in which generic types are preemptively specialized at compile time according to instances that may be required at runtime. This approach suffers from an inability to handle many useful problems in the class nomono, such as list permutation, as well as requiring costly static analysis to discover all possible instances and resulting in large compiled binaries. The Go team implemented generics in the March 2020 release of Go 1.18. This used a slightly optimized version of monomorphization called Hybrid, but does not fundamentally avoid the issues already discussed. Our work solves all of these limitations by introducing the first dictionary passing translation for generic Go. This presentation is broken down into 6 parts. We begin by introducing generics in Go, followed by our dictionary passing translation and proof of correctness. We will then describe our implementation and empirical evaluation, and finally wrap up by giving some thoughts on what this work means for the future of Go. Go and generic Go. Go is a structurally typed, object-oriented language, the syntax of which is based on C and should be familiar to anyone who's used that language. In particular, we consider a featherweight sublanguage of Go, which includes interfaces, such as function, which defines a collection of method specifications that any implementing object must possess. In this case, to implement the function interface, a type needs to define an apply method, taking a single argument of the any type and returning an any, where any is the empty interface. Structs are record types. In this example, greater than func contains a single field val of type int. Methods are defined on a receiver struct. In this example, an apply method is defined on greater than func, the type of which matches exactly that given in function. By Go structural typing, greater than func implements function. Finally, type assertions, or casts, convert one type to another. Here, the any typed variable arg is asserted to int. The validity of the assertion is tested at runtime, and if it is not possible, then a type assertion error is produced. The program entrance function, main, first successfully calls greater than func.apply on the integer 3, but when the string literal 3 is given to the same function, a type assertion error is produced at runtime. This because the assertion from string to int fails. Generics, also known as parameterized polymorphism, provide a clean mechanism to increase type specificity without compromising on code reusability. A key benefit of generics is that many programs that otherwise relied on runtime type assertions can be statically and efficiently checked by the type checker. Function now accepts 2 type parameters, s and t, representing the function's domain and codomain. Both s and t are bounded by the any interface. This means that these type parameters may only be specialized by types implementing any. In this case, that's not a very onerous requirement. The ORD interface, however, provides a somewhat more interesting type bound. Demonstrating f-bounded polymorphism, a form of self-referentialism, ORD ensures that for any implementing type, the argument to its greater than method not only implements ORD, but is of the implementing type itself. Greater than func is extended to include an ORD-bounded type parameter s. Because the generic greater than func.apply method uses this ORD-bounded type parameter for its argument, we can now use the greater than method specified by the type pound and safely omit the risky runtime type assertion required by the non-generic version. safe in the knowledge that the type checker will reject invalid uses. Invoking a method on a generic variable, such as this.val.greater is called a generic method call. Calling greater than func of int.apply with the int3 works desired, but calling the same function with the string literal 3 is rejected at compile time. We've successfully caught the type error statically rather than at runtime. We now move on to the dictionary passing translation. In this presentation, I will give a flavour of the translation and point to the source-to-source formalization in the paper for the more precise details, including a look at the unique problems involved in applying dictionary passing to a structurally typed language such as Go. Recall that type bounds specify the methods that a specializing type must possess. A dictionary is a map from method names to specific implementations. Concretely, a dictionary for the OR type contains a single method implementation for greater than. We may then pass this dictionary variable in place of type parameters, either as an extra struct field or as an extra method argument. Resolving generic method calls then simply becomes a case of performing a lookup on the relevant dictionary for a concrete method implementation. Once we have the dictionary passing translation, the first question is, how do we know it's correct? An initial approach to try is using the standard strong by simulation equivalence. This was the approach taken in the previous paper to show the correctness of monomorphization. A translation mapping, i.e. mono, from P to the map of P, forms a strong simulation when, for each transition that the source program can make to a state Q, there exists some state in the target language such that the map of P reduces to it, and it is the translation of Q. That is, each step in the source program is simulated by a step in the target program. For the mapping to be a strong bisimulation, the inverse must also hold. That is, if the translation takes a step, then there must exist a state in the source such that the original program P reduces to it, and it translates to the result of the map of P's reduction. That is, the translated program can only take steps in keeping with the source program. Unfortunately, the standard notion of bisimulation is not adequate to show the correctness of dictionary passing. Take the foo example, in which a generic method call on A is made, but only after some function bar is fully computed. Equally, the translated program can only resolve the generic method's implementation after bar is fully computed. To show how basic bisimulation is incapable of showing the correctness of this example, we consider a program which calls foo. Attempting to complete the commutativity diagram, we see that the reduced source program does not translate into the reduced target program, as the source has fully specified the method body of foo, whilst this target still needs to perform a dictionary lookup on add. But before it can do that, we would need to fully resolve bar. This is an undecidable problem, as we do not know if bar terminates. Previous work looking at dictionary passing has encountered the same problem and attempted to solve it by using bounded reduction techniques. These approaches cannot be sound and complete. We overcome these limitations by introducing a novel congruence relationship called dictionary resolution, represented here by the open arrow. The dictionary resolution relationship preempts method lookups. This is justified as the preempted reductions are non-effectful and deterministic. We can now complete the commutativity diagram. Rather than showing that after a standard reduction the source and target programs are equal, we've instead shown that they are equivalent up to dictionary resolution. Bisimulation up to dictionary resolution is given by the commutativity diagram. Finally, we get to our main theorem. The dictionary passing translation from featherweight generic Go to featherweight Go is type preserving. The translation of well-typed programs are well-typed. Forms of bisimulation up to dictionary resolution is type assertion error preserving. A translated program will throw a type assertion error if and only if the source does. And most importantly, is value preserving. That is, the dictionary passing translation does not change the final result of the program. Value preservation is a direct result of bisimulation up to dictionary resolution.
I am Shufei Zhu from Penn State. I will introduce the rest of the paper. We implemented two artifacts called dict and erasure, which are based on the core calculus of featherweight Go. Dict is a dictionary passing translator. Erasure is an alternative homogeneous implementation besides dictionary passing. Rather than using a dictionary, It erases the generic types and uses the underlying interface types. When calling a method, the erased object is dynamically cast to the corresponding interface and directly used as a receiver. Mono, Go2Go, and Go 1.18 are 3 monomorphization implementations, which are also included in the benchmark set. All of the 5 implementations lack support of certain generic features of the complete FGG. Go2Go and Go 1.18 are implemented by the Go team and target the full Go language. Such differences are shown on the Venn diagram on the left. Next, I will introduce how we evaluate the 5 implementations. We implemented 2 benchmark suites. The micro-benchmark programs evaluate whether and how the translated Go code scale with 5 different aspects of the complexity of generic programs. The real-world benchmarks re-implement benchmark programs from 2 previous papers on Java and Scala into Go with the generics. The 5 micro-benchmark programs are all derived from the base program. It enumerates all possible combinations of type arguments for F1. Function F1 takes 2 parameters and uses them to call F2, which in turn calls callbase. In callbase, ops represents 2 non-generic operations. All methods of interface base G1 and G2 are implemented by struct derived and are called from receiver variable X with the generic type base. Function main calls doit 10,000 times to provide stable performance results. Program A extends the number of methods of base and derived in the base program from 2 to n. We consider 3 metrics: code size, execution time, and compilation time. We found that monomorphization methods generate larger executable programs. For execution time, Dict makes faster programs than Erasure, but those programs are slower than programs generated by Mono and Go2Go, which didn't use dictionaries in their translation. For compilation time, Mono is significantly slower than the other 4 translators. The other 4 translators' results on compilation time are similar. Program E is particularly designed to expose the exponential complexity of monomorphization. The configuration parameter m controls both the number of type parameters and the number of functions called in between doit and base call. We find that both the code size and the compilation time scale exponentially for all 3 monomorphization methods. Dict and Erasure scale polynomially on the 2 matrices because they do not create an exponential number of copies of callbase for all type argument combinations. In particular, when m is large enough, Mono is slower than Dict in execution time due to catch misses. Now we introduce the results on real-world benchmarks. Overall, the translated programs of Dict and Erasure have a smaller code size but a longer execution time, which is consistent with the results on the micro-benchmarks. However, the compilation time does not change significantly across different translators, because all real-world benchmarks are small and do not have many usages of generics. Let me conclude the talk. First, we design, formalize, and implement a new dictionary parsing translation of Go. The translation handles structural typing and can translate nominal programs, which are beyond the capability of Go 1.18. Second, we prove essential correctness properties of the translation by introducing a novel and general bisimulation up-to technique. Third, we implement the translation and evaluate 5 different implementations. We provide useful implications from the evaluation results. For instance, we find that Go 1.18 is very conservative in its support for GC shapes, which future compiler developers can improve. You can find more from the full version of the paper, such as the proofs and the artifact.